Hello friends, Rahul Jha welcomes you. Today we'll be talking about smallest hard disk sizes. So let's start. What is smallest hard disk today? Of course, this is an excellent question because the term smallest can refer to very different things in the world of hard disk drives, HDDs. Physical size, form factor, the physical dimensions of the drive itself, storage capacity, the drive with the lowest amount of storage space available. Here's a breakdown of smallest in both categories. Smallest by physical size, form factor. The undisputed smallest traditional hard disk drive HDD you can buy today is 1.8-inch form factor. Dimensions typically around 54 millimeters by 78 millimeters by 5 millimeters or up to 9 millimeters thick for higher capacities. Interface. They often use a ZIF, zero insertion force, or micro SATA connector. Use case. These are famously used in Apple iPods, hence their nickname iPod hard drives. Other MP3 players and ultra compact laptops. However, they have almost equally been replaced by NAND flash memory like SD cards and SSD chips in consumer devices because flash is faster, more power efficient, and more shock resistant. Important caveat: while the 1.8-inch HDD is the smallest commercially available form factor, it is now a niche product. You won't find them at your average electronics store. They are primarily used for specific industrial embedded or legacy upgraded purposes. What about smaller than 1.8 inch? Technologically, there are there have been prototypes of and micro drives like the 1-inch drive or the CF2 form factor used in some early digital cameras. But these are no longer in production and were made obsolete by flash memory, the true smallest for storage. If we expand the definition of hard disk to include any device used for data storage, then the micro SD card is the true physical smallest. Modern micro SD cards can be as small as 11 millimeters by 15 millimeters and are available in capacities exceeding 1 TB. Smallest by storage capacity. This is more practical question for someone looking for cheap drive. The smallest capacity new HDD you can easily buy today is 500 GB drive. Form factor. This is almost exclusively found in 2.5-inch form factor, the standard size for laptops. Why they exist? They are manufactured as entry-level, budget-friendly options for basic laptop upgrades or external portable hard drives. While 1 TB is the current sweet spot for price and capacity, 500 GB drives are still produced for the very low-cost market segment. The trends. It is becoming increasingly difficult to find new HDDs below 500 GB. Drive manufacturers have stopped producing them because the cost difference between 500 GB platter and 1 TB platter is negligible and the demand for such low capacity is tiny. What about smaller than 500 GB? You would have to buy very old used hardwares, example a 20 GB drive from the early 2000s. These are not practical for modern use. Summary table. Category, winner, details, and typical use today. Smallest physical size HDD, 1.8-inch HDD, 54 by 78 into 5 to 9 millimeters. Industrial legacy system, old iPod replacements. Smallest common capacity new, 500 GB, 2.5-inch HDD, 2.5-inch form factor. Budget laptops upgrades, cheap external portable drives, overall physical smallest, any storage, micro SD card, 11 by 15 millimeters, phones, drones, cameras, Raspberry Pis, Nintendo Switch. Conclusion. For the vast majority of people asking this question, the most relevant answer is if you have a tiny physical drive for the project, a micro SD card, what you are looking for. If you need the cheapest, lowest capacity new hard drive for a computer, look for 500 GB 2.5-inch SATA HDD. How and where it can be used? Of course, manufacturing a modern hard disk drive HDD is one of the most complex and precise mass production processes in the world, often described as putting a 747 jet plane 1 micrometer off the ground while it is traveling at max speed. Here's a breakdown of how it's done and what's required from the macro view down to nanoscale, the core components required for manufacturing. First, you need the materials and subcomponents that go into an HDD. Platters, the circular disks that store data made from substrate, usually glass or aluminum alloy, coated with multiple ultra thin layers of magnetic material, example cobalt based alloys, protective carbon and a lubricant, read or write heads. The tiny components that fly over the platters to read and write data. These are marvels of nanotechnology built on wafers similar to microchips. Actuator arm, the mechanical arm that holds the read-write heads and moves them across the platters. Spindle motors, a high-precision motor that spins the platters at a constant high speed 5400 to 7200 RPM for consumer drives, up to 15,000 RPM for enterprise drives. Vice coil actuator, the motor that controls the movement of the actuator arm with extremely speed and precision. Printed circuit board PCB, the motherboard of HDD which contains the controller, processor, memory, cache and motor drivers. Base casting and top cover, the sealed metal enclosure that protects the internal component from any external contamination. A high precision manufacturing process. The assembly must be done in a class 100 clean room. This means no more than 100 particles larger than 0.5 micrometers are allowed in a cubic foot of air. A single dust particle is like a boulder on the platter surface and can cause a head crash, destruction of the drive. The process can be broken down into several key stages. Platter manufacturing, substrate preparation. The glass or aluminum discs are polished to an atomically smooth mirror-like finish. Any imperfection is measured in angstroms, 1/10 billionth of a meter. Sputtering. The polished platters are loaded into a vacuum chamber. Ions of the magnetic material, example cobalt, platinum, chromium, are bombarded onto the platter surface, depositing a thin, perfectly even magnetic layer only a few nanometers thick. Additionally, layers of protection and lubrications are added similarly. Head gimbal assembly, HGA manufacturing. This is a semiconductor-like process. Thousands of read-write heads are fabricated simultaneously on a silicon wafer. Using photolithography, the same process used to make CPUs, the microscopic elements of the head, including giant magnetoresistive GMR or newer tunnel magnetoresistive TMR sensors, are etched on to the wafer. The wafer is then sliced into individual heads, which are attached to a suspension arm, the gimbal. The gimbal provides the precise spring force and flexibility that allows the head to fly steadily nanometers above the platter. Drive assembly. The mechanical build. There is a highly automated process performed by the robots in the clean room. Base casting. The base of drive is placed on assembly line. Spindle and platters. This spindle motor is installed. The pristine platters are carefully stacked onto the spindle with separators between them. Head stack assembly. The actuator arm with the multiple HGS attack is installed. Cover sealing. The top cover is placed and sealed with a special gasket, the small breather hole with an internal filter equalizes pressure but keeps particles out. Servo writing and low level formatting. This is one of the most critical and time consuming steps. The problem: to know where to write data, the drive needs a map. This map, called the servo pattern, must be written before any user data can be stored. The challenge: you can write this map without a map. It's a chicken and egg problem. The solution: the drive is connected to a high precision servo writer. This is a massive ultra precise machine that uses external laser guides to tell the drive exactly where to write the servo tracks on the blank platters. This process imprints the physical roadmap onto the platters. This is done after the drive is sealed to ensure the map is perfectly aligned under the real operating conditions. Final testing and software loading. The finished drive is subjected to extensive testing, bad sector scanning, performance benchmarking, vibration and thermal testing. The drive's firmware is loaded. Finally, it is packaged for shipment. What is required for this manufacturing? You cannot build an HDD factory in your garage. The barriers to entry are enormous. Requirement description: ultra high capital investment. Building a state-of-art fabrication plant, fab, and clean room costs billions of dollars. The servo writers alone cost millions each. Clean room facilities: a massive vibration dampened, temperature controlled, class 100 or better. Clean room is non-negotiable. Proprietary and specialized machinery. This includes sputtering machine, wafer fabrication lines for heads, robotic assembly lines, and a critical servo writers. This machinery is not off the shelf. It's custom built for the handful of HDD manufacturers. Advanced material science. Deep expertise in metallurgy, magnetic theory, and tribology. The science of friction, wear, and lubrication is required to develop platter, coating, and head materials. Nanotechnology and precision engineering. The ability to work at a scale of nanometers is fundamental. This requires physicists, material scientists, and highly skilled engineers. Complex software and control systems. Writing the firmware that controls the drive, mechanics, error correction, and communication with the computer is extremely complex. Vertical integration. The three remaining HDD companies, Seagate, Western Digital, and Toshiba, control almost every aspect of the supply chain, from designing the heads to manufacturing the platters and developing the firmware. This is necessary to achieve the required precision and cost efficiency. Conclusion: manufacturing an HDD is a feat of physics, chemistry, material science, and precision mechanical and electrical engineering on the microscopic scale. It requires a monumental initial investment, continuous R&D to keep advancing. This is why there are only three major companies left in the world that do it at a scale: Seagate, Western Digital, and Toshiba. The entire process is designed to achieve one goal: reliably storing and retrieving digital bits from the layers of magnetic material just a few atoms thick. What can be next generation hard disk like this in future? Of course, this is a fascinating topic that sits at the frontier of material science and physics. The next generation of hard disk drives, HDDs, won't just be smaller, they will be radically different on the inside using technology that are currently in labs to achieve unimaginable densities. The primary goal of future is not necessarily to make physical drives smaller, but to dramatically increase storage capacity within a standard 3.5-inch form factor. The dream is to eventually reach petabyte scale, that is 1000 terabytes in a single drive. Here are most promising technology that can define the next generation of HDDs. Heat assisted magnetic recording, HAMR. This is not just a future technology, it's already here. Seagate began shipping HAMR drives in 2023-2024. However, it represents the first major step into the next generation. How it works. Traditionally, HDD can't write on extremely stable magnetic material because the write head isn't powerful enough. HAMR solves this by using a tiny laser diode integrated into write head to momentarily heat a microscopic spot on the platter to around 400-500 degrees centigrade. This heating makes the material temporarily more receptive to magnetic influence. The head writes the data and the spot cools down almost instantly, locking the data bit in place with incredible stability. What it enables? HAMR allows the use of new, much more stable iron platinum alloy media. This stability means data bits can be made incredibly small without them becoming thermally unstable and flipping randomly. A problem can be super paramagnetic limit. This is the key to dramatically increase areal density. What it looks like. The drive will look like a standard 3.5-inch HDD from the outside. The magic is inside the hermetically sealed, ultra clean enclosures. Bit patterned media BPM. While HAMR changes how we write, BPM changes the canvas we write on. How it works. Current HDD platters have a continuous magnetic film. Data bits are written as magnetic domains in this film, and they are starting to physically touch each other, causing interference. BPM uses a nano-patterned platter where each data bit is stored on a predefined, physically located, isolated island. Nanodot. These islands are created using advanced nanolithography, similar to how computer chips are made. Why it is better? This eliminates magnetic interference between bits, allowing them to be packed even closer together. It's like moving from a crowded, continuous field of people to a stadium with individual assigned seats. Challenge. Manufacturing these perfect nano-pattern platters at a low cost and high volume is extremely difficult. Microwave assisted magnetic recording, MAMR. Alternative to HAMR that uses a different energy source. How it works? Instead of a laser, MAMR uses a spin torque oscillator on the right head to generate a localized microwave field. This microwave field helps flip the magnetic bit by resonating with the electrons in the media, making it easier to write without heat. Status: Western Digital has pursued this technology. It's seen as potentially more reliable alternative to HAMR as it avoids extremely thermal cycling, but it has proven more challenging to scale to the same ultimate densities. Two-dimensional magnetic recording TDMR. This is an advancement on the read side of the equation. How it works: as data bits gets smaller, the read head becomes larger than the bit itself, reading multiple bits and noise simultaneously. TDMR uses multiple read sensors like having multiple ears and sophisticated signal processing algorithms like a brain to isolate the intended data signal from the surrounding noise. Analogy: it's like trying to hear one person talking in a noisy room. Using two ears and your brain TDMR, you can focus on that one voice, filtering out the crowd. The ultimate future: hybrid and revolutionary technologies. Looking further out, the line between HDD and SSD might blur, or entirely new paradigm could emerge. HDD SSD hybrids. We already have SSHD, solid state hybrid drives, but future versions could be more deeply integrated. Imagine a drive where the HDD section is usually used for massive cold storage, while a large fast SSD section acts as a massive cache and workspace, all managed seamlessly by the driver's controller. HAMR plus BPM combination. The true holy grail for HDD technology is to combine HAMR's writing ability with BPM's perfect canvas. This combination could push a real density to its ultimate physical limits, potentially enabling 50 to 100 TB plus drives and beyond within a decade. Non-magnetic technology, the real next generation. DNA data storage. Using synthetic DNA strands to store data, its density potential is mind-boggling. The entire internet could fit in a shoe box. The challenges are speed, very slow write read, and cost, making it only suitable for archival storage. Holographic storage, storing data in 3D pattern inside a crystal or polymer. This leverages volume instead of just surface area. 5D optical storage, using nanostructures in glass to store data in 5 dimensions: size, orientation, and 3D position. It's extremely stable for thousands of years, but is currently very, very slow to write. Summary: what the next generation HDD will be like. Features: today's HDD, CMR, PMR. Next generation HAMR, MAMR. Far future, HAMR plus BPM. Key technology: perpendicular magnetic recording, energy assisted recording, combined advanced technologies. Maximum capacity 24 to 26 TB, 30 plus TB, to 50 plus TB, 80 TB, and to 100 plus TB, that is petabyte class. Areal density 1.5 TB per inch square, 4 plus TB per inch square, and then 10 plus TB per inch square. How it works: writing on continuous film, heating, microwaving tiny spots, writing on pre-patterned nano islands. Physical form: 3.5 inch, 2.5 inch, same factor, next same form factor but smarter. In short, the next generation HDD won't look different on your desk, but inside it will be a masterpiece of physics and engineering, using lasers, microwaves, and nano-patterned material to store amounts of data that are unimaginable today. Its role will solidify as the ultra-high capacity, cost-effective cornerstone of the world's data centers and cold storage archives. This was all. If you have visited our channel for the first time, please like and subscribe our channel. Thank you.